Okay, in this video, we're looking at section 4.6 on isosceles, equilateral, and right triangles. So, first of all, an isosceles triangle, you know what an isosceles triangle is already. It's a triangle that has two sides at least that are congruent to each other. And so there's some important vocabulary that we need to know about isosceles triangle because we're going to be referring to it through our theorems here. And so the first is that the two sides that are congruent to each other are called legs. So the two sides that are congruent are the legs. The third side is what we call the base. Now, it is totally possible for an isosceles triangle to be sitting on a leg versus the base. So do not just assume that whatever side the triangle is sitting on is its base, because that's not always the case. So we have two legs and then the base. Those are the sides of the triangle. And then the two angles that are on either side of the base, so the base and both legs make an angle, and those angles are both called the base angles. And then the third angle, which is opposite of the base, is called the vertex angle. So we have those six parts of an isosceles triangle. And then we have what we call the base angle theorem, which again, I don't want you using the title of it. I want you to know what it says. So the base angle theorem says that if two sides of a triangle are congruent, then the angles opposite of them are congruent. So basically what that's telling us is in an isosceles triangle, we have two sides that are congruent to each other, the two legs. And so the angles that are opposite of those two legs are also congruent to each other. So in this example that I have here, if CA is congruent to CR, then angle A is congruent to angle R, so that the side or the angles opposite of the sides are congruent to each other. And so that's the base angles in both of those examples. Now we also have the converse of that, which says that if two angles of a triangle are congruent, then the sides opposite of them are congruent. So if we know here in this next example that angle N is congruent to angle T, then we can say that line segment AN is congruent to line segment AT because we have congruent angles, therefore we have congruent opposite sides. So a corollary, hopefully you recall, is something that just kind of naturally falls in place after we have a theorem. So a corollary to these two theorems, the base angle theorem and its converse, is that if we have a triangle that's equilateral, then all the angles are congruent to each other, so we know it has to be equiangular. And again, just intuitively, we know that that's the case. And then we have the opposite of that, that if we have a triangle that's equiangular, then it also has to be equilateral. All right. So I've mentioned to you before about how we only need two pieces of information really to prove that two triangles are congruent to each other. And I may have mentioned the HL theorem to you. So the HL theorem, H stands for hypotenuse, L stands for leg. So we are able to use the HL theorem because if we have a hypotenuse, then we know that we have to have a right angle because we do not have a hypotenuse of any triangle except for a right triangle. And the hypotenuse is the side opposite of the right angle. So the HL theorem allows us to use the hypotenuse and leg of a triangle to prove that two triangles are congruent to each other. So the theorem reads like this. It says, if the hypotenuse and a leg of a right triangle are congruent to the hypotenuse and leg of a second right triangle, then the two triangles are congruent. Now again, just like with all other triangles, you have to be very careful to make sure that the segments or the legs that match up are corresponding legs. Because if they're not, then we cannot use the HL theorem. So just like before with our triangles, we had to make sure that corresponding legs matched up together. And so the same is true here. So then in this example, I know that AR is congruent to AX, which I have labeled on the picture here. And then I know that ER is congruent to WX, which are both the hypotenuse. of the triangles. So since I know the corresponding legs and the hypotenuse are congruent, then I can prove that triangle EAR is congruent to triangle WAX. So those two triangles are congruent to each other because of hypotenuse and leg that are congruent. And so this is really the only angle side side, which remember we've talked about that that's not a good theorem, but this is, in this case, okay to use. But we use it as HL instead of angle side side. So if you look, there's a couple of examples that I'd like you to try. So this first one is finding the value of x and y. So I know if you look at the triangle on the right that has a 50-degree angle as well as angle x, that is an isosceles triangle. So if it's an isosceles triangle, what do we have to know about angle x? It has to be how many degrees. And remember, it's isosceles, so this angle x is congruent to this angle over here that I don't know yet, but I can definitely find out because it's isosceles. So once I know that angle x, I know the blank angle on the right, and then I should be able to figure out what angle y is, again, knowing that I have an isosceles triangle because these two sides here are congruent to each other. So please find the value of x and y for that particular problem. Then this next problem probably needs a little bit of explanation because I'm trying to draw a three-dimensional image in a two-dimensional space, which is difficult. And so if you think of that line TS as an electric pole or one of those poles that you see on the side of the road as you're driving down the road, that's what I'm going for here in this drawing. And then if you use your imagination a little bit, point P is behind that pole, and then point Q is kind of in front of it a little bit, and point R is over and behind it just a little bit. So it's a three-dimensional shape drawn in two-dimensional space. So imagine that you have, for example, a TP. And so you have the sides that come down that hold up that TP. And so if you kind of think of this as a little bit of that, use your imagination a little bit. And so I know that TS is perpendicular to the undrawn line segment PS. And I know that TS is perpendicular, to the undrawn line segment of QS. And that TS is perpendicular to the undrawn line segment RS. And I know that TP is congruent to TQ, which is congruent to TR. So if you think of it as, again, the TP, those sides or those posts that are holding up the edges of the TP are all congruent to each other. So then I want you to prove that those three triangles that are made are congruent to each other. It may possibly help you to take a pencil and make it perpendicular to a tabletop and then use three strings to draw, attached to your pencil and attached to your table to kind of give you a more concrete image of what that picture is. And we'll work on that tomorrow in class as well. But see if you can figure out that proof. Then here in example number 3. I know that GE is congruent to GT and that EO is congruent to TM. And I need to prove that OT is congruent to ME. Think about our segment addition postulate that we studied a long time ago. Think about what we know about congruent sides and their corresponding angles or opposite angles, really. So the base angle theorem that we looked at a few minutes ago. And maybe it might help you to draw apart those two triangles, maybe break that image apart a little bit so that they're not overlapping, and see if you can figure out, or at least get a good start on proving that OT is congruent to ME. Chances are we're going to use the base angle theorem. It is possible that we'll use CP/CTC as well in this problem. So see what you can do with those two problems. I think number 1 you'll be very successful with. I don't think you'll have a problem with number 2. Number 3 might be a little tricky. But as always, we will go through these problems tomorrow in class. Have a great night. See you tomorrow.